Ordering and interleaving. Sorry. All will be explained. Yeah. I'm okay, thanks. Most of my symptoms are gone. I still haven't heard back from the doctor about the barrage of blood tests, so there still might be a surprise waiting for me, but I can make a fist. The firearms above my head. Handwriting time holding back. Thanks for asking. It's just, it's one of these things, like I'm not a crybaby. Well, I'm a crybaby actually. But I just never felt those symptoms before, so I was like totally freaking out. I was like, am I going to wake up paralyzed here? So we're like very much in the thick of replication health, which is like a 2.5-year thing in this course. There's a set of protocols we study in low detail in this course. It's strongly consistent with replication protocol. So we're going to spend a bunch more time on the primary back today. We're going to work out some of the sort of subtleties that we didn't address in the initial presentation around like, the primary needs to decide what order these things happen and how does it do that. It's going to turn out that how it does that is very related to the first in, first out protocols that we studied in this class. We're going to take a little bit of time talking about how that might work in practice. And then sort of towards the end of the class, we're also going to take a little bit of time, spending more time getting honest about how do protocols like primary backup and as we generalize chain replication recover from failures, from the loss of backups, from the loss of primaries. Remain available despite those failures, because after all, that's the reason that we're doing this. In order to motivate chain replication, which is an alternative replication strategy to primary backup, I want to have a little bit of a definitional discussion around how we measure performance in distributed systems. Arguably, I should actually have a conversation a little early in the course, but now's the perfect time to get it out of the way. And then I'm going to dwell for some time on this cosmic thing about total orders over operations being necessary and sufficient to establish consistency. We're going to try to look at primary backup and say, okay, well, if every replication protocol establishes a total order, then there must be some way that primary backup does it, in some way that chain replication does it, in some way that quorum replication, which we're going to see a little later in the course, does it. And it turns out they all do it in different ways. But let's start with a little bit of just recap of the protocol at a very abstract level. Right? So primary backup is characterized by two principal roles, right? Primaries and backups. Okay? The role of the primary is more or less indistinguishable from a client to the role of a standalone single-site database server, right? I was talking about door of the database or whatever. It says, here's my API, you can perform reads and writes to name variables. The primary also exposes an API that says clients can do reads and writes to name variables. And the backups expose no APIs to the clients at all, right? Clients don't talk to backups. Clients only ever talk to backups through the primary as an intermediary. Right? So the picture might look like in a world in which we have one primary and two backups. Wait, by the way, why would I set up a world in which I had one primary and two backups? Why did I choose that number of things? Yeah. Yeah, well, in some sense, it's like, because I expect that two bad things might happen, and I want to still have one good thing there. In some sense, we talked about this a little bit in office hours. It's super common in replicated systems to model the world with a variable, big F, which is the number of crash failures that we think is going to happen. Now, that's not very realistic, right? Because we don't know how many crash failures are going to happen. If we pick some number, let's say 2, then there could be 3, and we'd be screwed. Nevertheless, it's useful to model the world in this way. So if I say, look, I think there's going to be 2 crashes, in general, in terms of F, how many replicas do we want? F plus 1, right? So 3 in this case, right? So in general, we're going to want at least F plus 1 replicas to tolerate F failures and still be able to do good stuff. And so the fact that there's 3, in some sense, is reflecting the fact that some system designer, configuration person, DevOps guy conjectured that 2 is the likely number of bad things. Had he thought that 4 was the likely number of bad things, we're probably going to have 5 backups, right? So that's why 3. It's sort of arbitrary. Okay? So, but client comes in the door. They want to write x equals 1. What does it look like? Primary. So they send it to the primary. do you know who the primary is? They might not. They might not. So one version of that is, remember we talked about views the other day? So let's imagine that the simplest version of this is, when the system starts up, there's this view, V1, that everybody knows. Don't ask me how. And V1 says, there's a primary, and that role is played by the person called P. And there's a backup 1 playing the role of backup. And there's a backup 2 also playing the role of backup. Now, if everybody knows that, and we can imagine a world in which everybody knows that, the client's got the message, then they know to address the primary. But just for shits and giggles, and since this came up in office hours, it's only fair to talk about it for a minute. What if the client didn't know who the primary was? What are some options we have in terms of designing a protocol? Say again? Well, it could send the message to everyone, but since it knows in the end it's going to have to just send it to the primary. Yeah.
The broadcast forward the messages to the primary?
Yeah, so an easier one that would be like a little bit nicer on the network. Well, the broadcast would certainly work if we were trying to. So what would be to say the client just picks a server at random, or it picks anybody that it can name, and it sends its request. Okay? But now, what do you think could happen? It seems to me there's two obvious design options. And those of you who are familiar with like DNS may be familiar with these options. There's sort of an iterative and a recursive way for V1 to handle this on C's behalf. Any thoughts on what you would do? Like, it can't, what can't V1 do? V1 can't just be the primary, right? Not in this view, right?
You can either tell the computer that what P is primary.
That's right. So approach number one, that you would call like the iterative approach, looks like this. V1 replies to C, and it says no. However, there's this guy named P who can do it for you. And then C goes for it. Advantage of that? Super simple. What's the disadvantage of that? It's a little bit of extra latency, because we had to do a round trip and a half. Right? What's the other alternative? Yeah, recursive, or what you might call proxy approach. Actually, very simple. It's like, I threw it with such violence, it turned into a cloud of dust. I don't know where the strength came from. Where was I? Very similar to what you're doing in homework 2, right? Which is to say, V1's like, well, I can't be the primary, but you don't know, like I can if I'm careful, right? If I just go ahead and forward x equals 1 to the primary, then the primary does their thing, they respond, and then I ultimately respond to the client. So I was just a man in the middle, right? This is nice because it means the client logic can be a lot simpler. And sometimes the other thing needed a fat client that knew how to handle the, anybody ever heard the term knack? So there's acknowledgements, we call them knacks. And then there's like, I can't do that for you, bro. And that's like a knack, right? So the client got a knack, and it had to know how to handle it. Whereas in this, the client's totally transparent. As far as it's concerned, V1 is the primary. It's just a little slow. Does that make sense? Now, why am I telling you all this? Just because these are the kind of questions that are going to arise, right? There's three ways that a client can know how to address the primary. It can just know, or it can be directed to the primary in one of these two ways. And this is what we do in practice. When would we do the first thing, where the client just knew? Well, typically, if the clients were in the same data center, if the clients were like application servers close to the backups and primaries, it doesn't really cost us anything. Every time we tell everybody about the new configuration, we tell them too. On the other hand, if these clients are edge clients, and there's millions of them scattered all over the world, and they're in your smart fridge and your phone and all this kind of shit, you don't want to have to send them. You don't want to have to get them all to act some update before you can move to the next view. So you would probably prefer one of these other approaches. I'm not saying all this to confuse you, but to try to separate the pure primary backup protocol from the various tricks we might need to apply in practice to make it work. Yeah?
The iterative method can also be useful if the client will send repeated requests, so that instead of forwarding every one of those requests to it.
That's absolutely right. So it gets a batching advantage. Everybody hear that? So if we're only doing one thing, the difference between iterative and recursive is not such a big deal. But if the client, the more complicated client now has some state, and they can remember, kind of have a lease that says, hey, this guy is the primary. After after that, the client could just keep sending stuff to that primary and save a round trip. Right? Yeah.
But perhaps in the recursive model, if in the response B1 will tell C that I did a request and P is P.
You could hybridize them. Absolutely you could.
Yeah.
Absolutely you could. And in fact, that might be a neat paper, right? That you're like, we always do recursive first because it's simpler, but then we can upgrade in some way to have a sticky memory of the primary. You could certainly have done a hybrid. You could certainly have done that. Any questions on this? Okay. So, as long as we're doing, let's be honest about primary and backup. Let's do the whole protocol end to end, and then let's talk a little bit about ordering and sequencing initially. So,
Quick question.
yeah.
Is there ever a situation where client goes to backup goes to primary, and then tells primary to get to client?
Well, I mean, so like, I'm going to stop it. So like, we can invent increasingly arcane versions of this. That one's going to be tricky because of things like TCP that they don't have a socket. No, but if we have RPCs, that's fine. In fact, we're going to see when we study chain replication that we have communication topology very much like that. So let me just like save that. Okay, but let's do straight ahead. Primary back. So client says X equals 1.
It's going to
Primary sends it to how many of the backups? All of them. The backups respond when they've written it to their local storage. Remember I talked about a commit point? Where's the commit point in the execution?
bottom right there, the B2 gives acknowledgement.
Yeah, when it's gotten unanimous agreement, and what does the commit point like mean?
The right
stores.
It means it's like
With
that
rights.
thing happened, right? The act of setting X to 1, we say occurred at the commit point. And before the commit point, there's uncertainty about whether it occurred. Now, when we know it occurred, we know we can tell the client that it was successful. Because we know it's been durably stored on more replicas than we believe are going to crash, right? It's always useful when you're studying a strongly consistent replication protocol to compare the executions to sort of the canonical executions that you would get if the database weren't replicated. And you always want to be able to say, from this side of the veil, from the client side, it looks the same. Even though it's obviously much more complicated here and probably a little bit slower here too, right? And so, X equals 1. Now let's just imagine we talk about this in off hours. This is a little bit of computational delay setting X to 1 because we have to spin a disk around or something like that. And here's our commit point when X is actually 1. When if somebody reads X, they'll get 1. That's a commit point. So this picture and this picture are the same picture, except that from when the message is received to the commit point is attenuated. Does everybody buy that? So in some sense, if we had a picture like this, and the client sent X equals 1 to DARS, and then doesn't hear back, the client doesn't know whether X was set to 1 or not. The client might need to set it again. So similarly, if we lose a backup or something goes wrong and we never get our acknowledgement, we don't know if the commit point was set. But that's not any more problematic than what we have in a client-server scenario where we don't get the acknowledgement after some amount of time. Right? Does that make sense? Why can't the client talk to the backup? Why do we not allow the client to talk to the backup? It would be faster if it could, right? Yeah.
There's no way for the backup to know when the commit point is happening.
The backups don't know when the commit point is, so what they do is, to keep the protocol simple, they sort of just commit eagerly, which means that they've revealed a write from the future, right? And as I showed you, let me see if I can do this with colored chalk, what we're concerned about is the following. That this client could say, what is the value of X, please? And this backup could say, X is 1. And let's imagine that it was initialized to 0. Okay? And then that same client could immediately ask the same question and see the value of x go forward in time and then back in time. Right? So this is stalemate. Something that would never happen if I was just talking to Doris. I would either read what I wrote or the thing before I wrote what I wrote. Time only moves forward on one timeline. Got that? Yeah.
So I'm a little bit confused about one thing. So if the primary sends the request to B1 to back up to like some value like x equals 2 or something, and it sends that same value to B2 with x equals 2. If B1 goes ahead and sends an ACK back to the primary, but B2 never responds again because B2 just crashes, then wouldn't B1 have the value of x equals 2, and then the primary would still think that everything failed? So
Yeah, no, that's great. That's a great question. Let me just, instead of getting disorderly on this picture, let me just draw a whole new picture for that. Okay. We had a client, we had a primary, we had backups 1 and 2. And in your world, backup 2 crashed while the protocol was going, right? So the x equals 1, now this backup actually thinks that x equals 1 from that point forward, right? But this backup crashes. I don't even really care when it crashed. But I know that we're never going to reach the commit point, which means the client's never going to get an acknowledgement. Which means at some level, just like over here, that shit never happened. X equals 1 never happened. Okay? That means that B1 at some point is going to need to be disabused of its belief that x equals 1. Right? Now, as I indicated in the last class, in general, in distributed systems or in systems generally, when you have a compound piece of work, I want to do A and B, but you have partial failure, you could do A and then fail and not have done B. Right? So in general, when you have compound work, work can get like partly done and left partly done. And when you have work that's partly done, you sort of have 2 options. What are they?
Only ever again and pick up where you left off.
Well, finish the work, or make it like this should never happen at all. So like roll forward or roll back. Which is the right decision is going to depend on the system and what the cost of throwing away work is. But in general, it's more complicated to roll forward. It's easier to get it wrong. It's more costly to roll back. You might have to do the same work over and over again. Does that make sense? It's one of these really important things we usually don't talk about until later in the class, which is trade-offs. So in systems, sometimes there's like the right way to do things. Sometimes you have a problem, you just pick the protocol for the problem, and life is good. More often than not, you have this space of trade-offs. I want to have my cake and eat it too. I want it to be fast and correct. You know? And in general, it's a zero-sum game. So this is one of these things where we're navigating a trade-off space. It turns out that for replication protocols, we're almost always going to favor undoing the work and making it look like it never happened and keeping the recovery simple, even if it means throwing away work. Right? So what that means is, when we go, let's say, so this was the world in which, let's say, backup 2 failed. So this is failure event that says, okay, backup 2 failed, and we're going to transition to this new view, V2, briefly, in which P remains the primary, and backup 1 is a backup, and we have no other backup. Now, obviously, we don't want to stay in this view for very long. We want to add a new backup, because we're getting really close to losing our data here, right? But we briefly are going to be in this view. So what happens? Let's see. So, this is the easy case, right? This write was essentially tentative. After the recovery, the primary tells, let's see. After every view change, the backups check in with the primary and ask it what is the highest numbered thing that it's done. And backups are going to throw away anything that's higher than what the primary has done. Now let me explain what I mean by numbered. That is this business. Yeah, but at a very high level, to answer your question, when everybody recovers from the view change, this backup is one operation ahead of the primary. The primary's memory is the memory of record, and we have to make this guy forget anything that it's written to its disk that the primary doesn't already know about. Now it's much more complicated when it's the primary that fails, because then we choose a new backup as the primary, and the cutoff mark just has to be whatever that backup has seen. Yeah, so that's a tricky case, yeah.
So in that case, it doesn't matter if the client sees that an operation fails, it still succeeds.
Well, the client never sees, remember, an operation failing, as I indicated over here. It just doesn't see the acknowledgement. And in general, this is hard. Right? This is hard even when we don't have a replicated database, because if what the client, remember our conversation about item focus, if what the client was doing was incrementing x by 1, it says increment x by 1, and waits for an acknowledgement. And it doesn't get it, and it waits, and it waits, and it waits. So now one of two things happen. This server crashed or rebooted, that obviously happened, right? Well, or it's just slow. Let's just say it did crash. It crashed either after doing the incrementation or before. But you don't know which, right? So what do you do? Well, you're probably going to send it again. The problem is you might increment the thing twice. And that's fundamental, right? We saw, I did an argument where I kind of showed that as a corollary of two generals, this is kind of fundamental, right? You could then number this, and you could remember the numbers, but then you run out of space. It's kind of fundamental. If you send something and you never hear back, it either happened or it didn't. And in some sense, that's orthogonal to the problem of strongly consistent replication. That just has to do with communicating over an unreliable medium. Okay, let's talk about ordering. The first point I want to make is every strongly consistent replicated system that we are going to study in this class, I should say, just to be defensive, achieves strong consistency by establishing a total order over all the operations. And as we've already discussed, when we're looking at replicated systems, the only operations that are in play are reads and writes to named entities, right? So I'm saying x is 1, I'm reading back the value of x. Right? Those are the operations, reads and writes to named thingies. So, based on everything I just said, if primary backup is strongly consistent, and it is, I'm telling you, then it is strongly consistent because it establishes a total order over operations. So the question that you should be asking yourselves, and that you will be asked on exams and things like this, is exactly how does primary backup establish a total order of operations? What is the order? Who decides it? How does it work? You can just take it at face value that it chooses a total order over operations. I promise. That's exactly it, right? So who chooses it? The primary does. Chooses it based on what? Based on alphabetical ordering? No, based on the arrival order. Can you imagine you could have a lot of different clients concurrently sending a lot of different things, with them all racing each other in wild ways. But the bottom line is because P has one line, and every arrow can only touch one place on one line, the touchdown of the arrows establishes a total order. Right? In exactly the same way that Doris did. Right? Arrival order at Doris, arrival order at the primary. The primary is just Doris. He just has a chorus of people that he's talking to. Yeah?
Is it correct to say that the order of commits are
No, that's a great question, and that's like a super important question when we get into what's called transactions. So this idea, we're going to study it a little bit in this class, that comes from the database community of, well, what if I wanted to like atomically update X, Y, and Z in such a way that they all changed or none of them changed? When you start to do multiple things like that, it doesn't make sense to talk about the order in which all things happen until you talk about the commit point sort of after the fact. Now by contrast, in primary backup replication, we don't need to reason about the order in which the commits happen, because there's no uncertainty, like everything always commits. So because everything always eventually commits, we can choose the ordering really early. So in some sense, like the primary chooses the order immediately when the things touch down. And so it doesn't matter what order the commit points happen in. Now, I'm going to give you an example.
Wouldn't the commit points happen in the same order?
Not necessarily. So let me give you an example of two different ways that you might implement ordering for primary backup and show how that's sometimes true but not always. Okay? So remember when we studied FIFO, that we studied two ways to implement FIFO. Like a super simple, but arguably not very fast way, right? In which we said, you send thing number 0, and then you don't even send thing number 1 until you get an acknowledgement that thing number 0 has been processed. Right? So in some sense, you don't send the thing until you know the pipeline is empty. That works, right? then we send number 2, and so on. But we also saw a somewhat more efficient approach to this, right? Where we just said, well, at the cost of a little additional complexity at Alice and Bob, we could have Alice just spray the area with messages without having to wait for any of the acknowledgments because she's gone ahead and put numbers on them. And the numbers are sufficient for Bob to know what order to replay them, and Bob doesn't care if some of them get reordered or whatever. Right? So what's the difference between this and this? This is super simple, but it doesn't make us good use of the network. Right? We're not pushing as many bits through the network for any time as we could. Whereas this one requires us to reason about counters and additional metadata, but does a little better. And so what I'm going to argue is when you think about how primary backup works, you could implement primary backup using either of these. And either of them will be correct. This will be the easier way to teach it, because it's less cluttered. But this will be the way you do it in practice, because it's much more efficient, right? So like one version of that is, this was request number 1. And I just don't even do, or the primary doesn't even do, so like the client comes in and says, now I want to set, I don't know, y equals 2. The primary could just say, well, I'm in the middle of something. I'm going to put y equals 2 on a queue. And when I get to my commit point and I'm not in the middle of something, then I could do my y equals 2. And that would look very much like this picture. And in this picture, yeah, sure. It's 1-to-1 between the order in which the primary sends things out and the commit points. They're kind of proceeding in lockstep, right? Because you get a request, you have its commit point. It's not until after the commit point of the first request that you have the next request, you have its commit point, okay? But you could also imagine, and in fact you probably would do this in practice, that, I have a client, he sends x equals 1, and then he sends y equals, let's say, 2 to the primary. And what the primary does is, the primary broadcasts these messages to the backups using this implementation of FIFO delivery. Right? So the primary says, item number 1 is x equals 1. And sure, it doesn't acknowledge that particular request until it gets these things. But it can immediately send out this request, which might even get to some of the replicas in the wrong order. It says 2 is y equals 2. But the fact that it got to the replicas in the wrong way, we could even imagine the commit point coming back here. So we decided that x equals 2 got written after, before. Right? So that it doesn't matter when the commit points happen because the order in which the writes are reflected on the stores is chosen by the primary and universally reflected by the replicas. And in practice, you always do this because, and this is a good transition, into a brief definition of the ways that we measure the performance of a distributed system, which hopefully will be reviewed for many of you. Can somebody give me a working definition of latency?
How long things take.
Particular action to complete.
Yeah, that's a great. So how long it takes a particular action to complete. So like time between invocation and completion of a single action, right? Single action is important, right? Because when we're measuring latency, we're measuring like the experience of being a client of one of these things. How long does it take between when I do my write and when I know that the write was stored? Or how long does it take between when I do a read and when I know the value of the thing that I read? Right? What about the throughput of the system?
How many actions?
How many invocations and completes we can get for each time?
Yeah. Or even more abstractly, just like number of actions per unit time. Sometimes you measure throughput in terms of actual like bytes pushed through the network or something like that per unit time, but we can just use actions as a proxy for that. Now, obviously, throughput is trying to measure something about the capacity or how much work the system can do. Whereas latency is trying to measure how slow it seems to be, right, to individual users. So like, is it meaningful to talk about like aggregate measures of throughput? Is it meaningful to talk about like average throughput of something? Sure, why not? I mean, you could get more sophisticated measures, but I'm sure be interested in the average throughput. What about max throughput, min throughput? Sure, why not? Yeah, because this is really, we're measuring this aggregate thing. There's lots of actions trying to share this system, and obviously a good system is a system that can like accommodate the maximum number of actions, or that the system that can keep accommodating more actions until you like fill up the bandwidth of the network and you can't push any more bits around or something. What about latency though? Is it meaningful to talk about like average latency and then max latency?
Depends on the context.
Depends on the context, so but go on.
Well, we want to know average latency, so that we want to know how long it takes a message to send and return on average. But if we're in a situation like primary backup, we want to know a lot about maximum latency.
Yeah, I totally agree. So like, because latency is something that's perceived by individual operations and sort of by extension by individual clients on the peripheries of these systems, it doesn't do me a lot of good. You know, typically the distribution of latency at something like a Google, let's say, is a long-tail distribution. You know, where like almost everybody gets their answer so fast that they couldn't even time that it was so fast. But every now and then there's somebody way out here in the tail who like, it takes like 10 seconds to get that search result. And this is like the kiss of death for something like Amazon, because like if I'm trying to check out something in my shopping cart and I click something and it takes like a couple seconds, I'll probably just give up, go shop somewhere else. And this actually translates to revenue for companies. So if you told me, but bro, don't worry about it. I know it took you 10 seconds to buy those Birkenstocks, but like on average, users are only there for a fraction of a second. There you go, thanks a lot. I don't care. Like, you know, average is scant comfort for somebody who's way out in the tail. So when people measure latency, they want to look at, well, what's the worst that it could be? But more often than not, they want to build some like little histograms out here and say like, what is the population of the buckets way out here? How many users are out here? And then when you're doing debugging tools and tracing and things like that, you really want to be like, okay, I just want to know how many people hit this bucket. But for all the people who hit this bucket, I want a log of like everything that happened, because I want to know what the hell went wrong for those like that fraction of users who get like the really bad experience. So what's the takeaway from this? Throughput is an aggregate measure performing how much work a system can do. All our ways of reasoning about things in aggregate make sense with respect to throughput. Latency is a measure of individual request response, and aggregate measures of throughput usually don't make sense. Okay, why did I say all that? Well, because these strategies. What would you say about this with respect to throughput and latency? Does this system exhibit probably higher throughput than this system, or lower throughput? Much higher, right? Like much higher. Yeah. Where throughput of this is going to be bounded by how many messages can be in the network at the same time. Which presumably there is some upper limit to that, but I don't know if we can hit it with our crappy app in Python, right? Whereas this one, obviously, the throughput is limited only by the latency. Like the throughput is limited by how long it takes to bounce back and forth. Okay? What about the latency of this system?
It's unchanged.
I would expect that it would be unchanged.
It might be.
Like latency sort of, you know, we haven't talked about ACKs in this picture, so I don't even know what the latency profile is, but the point is that by doing this trick, I massively increased the throughput, and it would appear that I did it without having a latency penalty. Right? When I talked about trade-offs before, it's often the case that it's like, what do you want? High throughput or low latency? Because you can't have both. As we'll see in a minute. All right. Did that? I think I did this. Yeah, I did that. Cool. All right, let's talk about shader. Yeah.
Before you move on from memory backup. Earlier you said when implementing total order, we're in this world where everything gets committed.
Yeah.
So, I mean, it seems like we're not, what if messages get lost, what if the backup crashes, that sort of thing? What happens to the total order that the primary hits?
Great.
Does it just roll back?
Great, let's talk about that for a minute. So, what happens if messages can get lost? Well, I think I have a really glib answer to this, which I encourage you to think more about offline. online and argue with me on Piazza, but if messages can get lost, we'll run some reliable delivery on that thing. Okay? And so I'm not going to worry about messages getting lost unless you come up with some reason why I should. So yeah, we can either say we're in the crash model, and we just think in the crash model if that makes our lives easier. Or we say we're in the omission model. Oh, and by the way, you also put some reliable delivery between every pair of things. Okay. If backups crash, the whole system grinds to a halt, and we have to do a reconfiguration. Now, as I indicated, but let me just say it again, to do a reconfiguration, we need quite a bit of machinery, right? We need a system. It has to comprise a number of machines so that it's fault tolerant. So it's like a cluster of servers who are talking to each other in a fault tolerant and scalable way. It turns out they're going to implement a protocol family called consensus that we're going to study later in this class to make sure that they are all on the same page, even if some of them might crash. And in addition to being on the same page, they need to implement failure detection because they need to collectively decide this backup's down, it's never coming back, or the primary is down. Failure detection is a hard problem that we're going to study later in this class. Don't worry about it right now. And they need to implement reliable broadcasts because they need to make sure, and atomic broadcasts, because they need to make sure that when the view changes, everybody gets the update. And everybody kind of stops what they're doing until they've applied the update. So you put all this together, it's consensus. You have a commit protocol. You have a failure detector. It's basically everything that's hard about distributed systems is going to be in this cluster of servers that handles view management. So what I'd ask you to do is like suspend your disbelief for another week and a half. Just imagine that it's God that's disseminating the view messages. And then we'll study in detail how you can implement all these things using Paxos, okay? But that said, if a primary or a backup fails, everything screeches to a halt, God comes down from the mountain, rearranges the roles of the servers, no work happens while that's happening. After that happens, as we discussed before, any half-baked changes that are on backups but not reflected on the primary are gone. And we start. Does that make sense? I know there's a lot of like moving parts there.
Like Tor stops at the last like working commit, and then you just kind of
It's
wait
a good
and
point.
fix it.
Anything that didn't make it to here never happened. That's the easy case where the primary didn't crash.
Right.
When the primary crashed, we need to decide where that would have been on the back. I'm going to send you a paper about this stuff, but it's it's edge case stuff. This isn't stuff we need to study for this class. Okay, chain replication. Yes. So, primary backup's pretty cool, right? It's like pretty simple. It works because the single site version that it is imitating works. Right, so it's just about, assuming we implement it correctly and we're careful and we dot our I's and cross our T's, it's just about the easiest distributed protocol to convince ourselves is strongly consistent. Because all we need to do to convince ourselves it's strongly consistent is throw a blanket to the right of P and say every behavior that P could have is the same as the behavior that Dart has. P behaves like a single site version of the thing, which means we're good. But it's not all good, right? Primary backup actually kind of sucks for a number of reasons. Why does primary backup suck? Well, so that's true. So in exchange for the degree of durability that this gives us, we have to wait for all the acts, which means this protocol is very susceptible to